Welcome to today's live broadcast, Prop 65 Trace Metals Workflow, from sample prep to the right answer. I'm Ryan Boyle, the Western Region Manager for Milestone, and I will be the moderator for today's event. Just a few housekeeping notes before we get started. If you have any technical issues, need help with anything, please use the raise hand option at the bottom of the screen and we will help assist. Also, the webinar is being recorded and will be available in the future should you wish to rewatch or share with a colleague. Today, you will hear from Milestone and Agilent on best practices for Prop 65 metals analysis, taking us through the entire workflow from sample prep to analysis and finally data compliance. I would like to introduce today's speakers. I'm joined by Eric Farrell from Milestone, covering microwave digestion, along with Craig Jones and Emmett Safi from Agilent, whom will dive into all things ICP-MS. Eric is the application specialist and will review sample preparation using rotor-based and single reaction chamber microwaves. Craig, who is an applications engineer, will cover day-to-day operations of your ICP-MS. Emmett, Agilent's ICP-MS product specialist, will talk more specifically about compliance and how that relates to ICP-MS. This webcast is interactive, so I encourage you to ask questions. We will have a Q&A session at the end. At the bottom of the tab, there is a Q&A button. So click there to ask any questions that you would like to have answered at the end. And then with that, I'm going to pass it off to Eric to get us started.
Hello, everybody. Thank you so much for joining us today and welcome to our webinar. My name is Eric Farrell, and I'm the product specialist here at Milestone for microwave digestion and clean chemistry. Today, I'll be giving you an overview of the various digestion solutions we offer, rotor-based and single reaction chamber for nutraceutical laboratories. And hopefully you'll be able to see the advantages and features of each platform, and hopefully you'll be able to see which might fit well into your laboratory to process your samples for Proposition 65. So before I get into the technology, I do want to talk a little bit about the challenges that you may be facing. Nutraceutical labs typically encounter a diverse range of sample types that come in, whether they're raw materials or it's a final product. Some of those final products may be gummies, prostate capsules, vitamin tablets, turmeric, even more difficult samples such as fish oils. Many times you may have to work with a larger sample mass. Larger sample masses are typically required when you need to make sure you're reaching low detection limits in a certain sample that you have, or to make sure that you're working with a homogeneous representation of your sample. Many of the samples that you may encounter may also have a rather high organic content, especially your oils or anything that's higher in protein. And any samples that are of this nature are typically quite reactive. Some of them may produce exothermic reactions and also generate a lot of pressure. We need to do all of this and process our samples and get complete digestions while making sure that we're meeting our regulatory requirements for Proposition 65 and testing for all of our metals of interest. And of course, Nutra labs are very, very busy environments. So you want to have a digestion solution that's not a bottleneck, but integrates into a streamlined workflow in your lab where you can weigh out your samples, digest them, dilute them up, and put them onto your ICP-MS. You want to make sure that you're meeting your throughput demands with your technology, however many samples you have to do per day, per week, per month. And also if you have any turnaround time expectations that you need to make sure you accommodate. So various different things to consider. So next we're going to go a little bit into microwave digestion workflow and some of the things that can affect that. So when you're looking to choose a digestion solution for your lab, there's a few questions that you want to ask yourself, and these are rather critical to make sure you get the right system for your needs. You want to understand what your sample types are, what are your elements of interest based off of Proposition 65, what is your acid chemistry that's required, what temperatures will be required for digestion and what are the pressures generated. So consider here working with organic samples, higher masses may lead to generating higher pressure. Also, some organics do require higher temperatures than others. So you want to make sure that whether you choose a rotor-based platform or the single reaction chamber, that you can achieve those complete digestions. Also, what are your throughput needs? How many samples per day, per week, per month are you doing? And do you see that changing over time, or is it going to be static? And also, what are your turnaround time expectations? Once you get a sample in, how quickly do you have to churn out that data? So not only do you want to be able to process your samples and get complete digestions, but you also want to make sure that you can do it in the timely manner that you need to. So we have two different microwave platforms to accommodate the needs of nutraceutical laboratories. The first one I'll speak about is our Ethos Up rotor-based platform. And then we have the next step up from that, which is our ultrawave single reaction chamber technology. So the Ethos Up is a traditional rotor-based system where our samples are processed in batches. If you take a look at the system over here, it's full stainless steel construction. We have two contactless sensors that live in the bottom of the microwave. And with the large cavity here, we're able to accommodate three different rotors: a high pressure rotor, high performance, and a high throughput rotor. So it's quite flexible, and you're able to interchange between any of those that you need to. Let's go ahead and take a look at the rotors that we have for the Ethos Up. The first one I want to show you over here is our Maxi 44. Our Maxi 44 is our high throughput medium pressure rotor, typically used for environmental applications. But as far as the needs of a nutraceutical laboratory, it's great because it has pretty high throughput, but you're going to be a bit limited on the sample mass that you're able to do for organics. So you might be limited to, say, about a quarter gram or so, maybe half a gram at the most. Then, if we look at our other rotor over here, on the other end of the spectrum is our SK15. Our SK15 is our high pressure rotor. This is fantastic because this can process all the different types of samples you'll be coming into in your nutraceutical laboratory. So not just some of the easier supplements, but also a lot of the higher organics, oils, things like that you'll be able to do in this rotor. Though it has the higher capability, higher temperature and pressure capability, 240 C and 100 bar, it's only 15 samples. So if you're quite a busy laboratory environment, 15 samples might not be enough to really support your throughput needs. So thinking of laboratories such as yours that have the need to digest more samples than say a 15 position rotor can handle, and the need to process higher masses than you can do on a high throughput medium pressure rotor, Milestone came out with the Maxi 24 HP high performance rotor, which is this here. The reason we came out with this was to blend the high pressure capabilities of the SK and the high throughput of the Maxi 44, while also taking the ease of use aspect from the Maxi platform of the Maxi 44. So with all three of our rotors, we're able to digest a single sample up to the maximum. There's no minimum number of vessels, but I'm going to focus in on, for now, on the Maxi 24. So the Maxi 24 can use a single vessel up to 24. You place your vessels anywhere in the carousel or the rotor, and there's no specific need to balance the rotor. This rotor is self-balancing. The vessel construction is quite simple. You have an 80 milliliter TFM vessel. It can be placed right on the analytical balance, and I'm going to show that to you. You have a top that goes on top, and then you have a cover. And then simple hand tightening is all you need to do this. There's no torque wrenches required. That's all the tightening that's needed for that. So this will work for pretty much any of the nutraceutical samples that you're going to be working with. However, on occasion, if you do have a sample that's a bit more difficult, say a fish oil or something of higher organics that may be just too difficult on the Maxi 44, then you may want to have a few segments of the SK15. But it's important to note that the Maxi 24 HP is the only 24 position rotor out there with the ability to go up to 220 C and 60 bar of pressure. There's no other rotor that's currently out there that does have these types of capabilities. So it is rather unique for Milestone. and a very good solution for nutraceutical laboratories because it can give you the ability to digest, say, higher masses of organics if you have to reach lower detection limits or you need a homogeneous representation. You can use that here. With the highly flexible Ethos Up platform, it can be provisioned to use all 3 rotors. If you can do 90 to 95% of your samples on here, and a few of the more difficult ones on the SK15. You can even get a partial rotor if you needed to. SK15 is a very good tool to have on hand if you do need it, but Maxis 24 is really going to be your best friend to meet your throughput requirements. So now I'm going to show you how we weigh out a sample and we do a digestion. So we're going to move over to my balance. I'm going to take my vessel over here. So the vessels weigh about 156 grams. So if you have a 200 or 220 place, 200 or 220 gram balance, that will work just fine for that. Here I'm going to take an iron gun. I can weigh my sample directly into the vessel here. I get my mass, and then next thing we would do is I would add my acid. However, I'm just doing a demonstration, so I'm going to add some DI water. This is how you would add your acid to the vessel. Minimum reagent volume on all 3 rotors, including the Maxi 24 HP, is 5 milliliters. So once I do that, I would undo the fume hood. I would place my cap on, tighten my rotor, my segment, like so, and then this would be placed into my rotor body. So I'm going to zoom out, and I'm going to put the rotor into the microwave so you can see that how that works. Open my microwave. I'm going to grab my Maxi 24 rotor, place it right on the front. One thing I do want to show you about the Maxi 24 that's very useful, together with the Ethos Up's large cavity, is it allows me to put the rotor on the front ledge. So I don't have to take the entire rotor body out every time, nor do I have to put the entire rotor body in every time. It can get a bit heavy with 24 samples. So I can put my sample in just like that, rock it to the back. When I'm done with my digestion, I open it up, I can rock it forward, take my sample out, bring it over to the fume hood, and dilute up to final volume. I'm going to go ahead and close this, and close the door. Once I've done that, I come over to my terminal. Ethos Up uses a dedicated terminal detached from the system. There's a library of over 300 pre-installed methods, so these will really give you a good starting point of where to start for your digestion runs. You can load right from there, and if you have a question about how to digest any samples, you can always ask us. Load your method, and then you simply press start. So once you press start, this light's going to turn red, and then when you're all completed, it's going to turn green. And then you can take your samples out and dilute them up to final volume and run them on your Agilent ICP-MS. The rotor-based microwaves have been around for well over 30 years, and they're the workhorse of the lab. They do have some limitations inherent to the technology. The need to batch similar type samples together of similar reactivities. You can only go so hot for so long because you're limited by the melting point of the polymer material, which comprises the rotors. Also, there is that vessel assembly and disassembly required. So with a rotor-based system, though it may automatically cool off, when you go to open up your vessels, you do need to depressurize each individual reaction vessel under the fume hood. And also, depending on your detection limits, you may require some additional cleaning of your vessels. So in order to overcome these limitations of rotor-based technology, that's where we came up with the single reaction chamber. So the single reaction chamber system was initially released as the UltraClave in 2006. 5 years later, we came out with the UltraWave in 2011. The UltraWave is a smaller benchtop model with full acid compatibility. You can use any type of acid, all with vials with loose fitting caps. And the way this technology works is quite different than a rotor-based system. So I'll give you an overview of how that works. With your rotor-based system, instead of having individual reaction vessels, we have a 1 liter stainless steel reaction chamber. Inside, we have a base load of acidified water, which is placed into that reaction chamber. Which I'll do right now. Instead of using reaction vessels such as this, we are now using vials with loose fitting caps. So there's no vessel assembly or disassembly required for this step. The reason we're able to do this is because we pre-pressurize the system with 40 bar of nitrogen before we even start the digestion run. This raises the boiling points of all my reagents and prevents cross-contamination between the samples. Let me show you some of the components we have on the ultrasound. For the filling of the nitrogen, you can either do it manually or use an automatic gas module, which I have here, which completely automates the filling of the nitrogen. I'm going to show you in a demonstration digestion how the workflow goes from weighing out the sample so you can see that work. The external chiller and the tank can be stored in the same room. Mine happens to be in a back room. Maybe if you don't have the space for it, that's fine. I can plumb them right through the wall right over here. So let me show you some of the workflow of how this works, and then I'll demonstrate this. So first we lower our samples into the reaction chamber. We clamp it. We pre-pressurize with 40 bar. We start our microwave program. Then we, once our microwave program is completed, instead of using air cooling passing across rotors, the ultrawave is going to use that external chiller, which is going to cool down the system faster than you can with a rotor-based system. And not only that, it's going to automatically depressurize. So the need to have to do this with a rotor-based system, that is not necessary with the ultrawave because it will automatically depressurize. Once it's automatically depressurized, the system will open up. You can take out your samples and dilute them up to final volume. So let me show you a little bit of what I have here, and let's do some samples. So, because with the ultrawave, great feature of this is all samples are at the same temperature and pressure conditions. That allows me to run mixed batches. So any of those samples that I may have had to run previously in separate runs, I can do them all together in the ultrawave. So this is a diverse, quite diverse collection of samples. Let's show you what I have over here. But as you can see, you can take any type of sample, run them together. They can be different masses. You can also have different acid chemistries. If you're running mixed batch samples, what we do is we choose a microwave program to digest the most difficult sample. And the rest of the samples come along for the ride. So let's go ahead and weigh out a sample. Here's some of the ones that we have. I'm going to choose from one of these. So I did some shopping. We have calcium, iron, CoQ10, B12, fish oil, which can be difficult, highly reactive. Also turmeric, vitamin E, and a 1-a-day men's vitamin. So let's look at my analytical balance. So weighing out a sample is as simple as taking my pedestal, placing it onto the balance, take my vial. We have different types of vials. We have disposable borosilicate glass, quartz, and TFL. I'm going to take one of my pills, drop it right into the top. Once I get my mass, I dilute up my sample. Excuse me, I add my acids, my reagents. This is just water. Then I place my loose fitting cap on it. Once I've done that, it goes right into my rack. I want to show you this other rack I have too. So in addition to the rack that you just saw, this one here is our 15-position rack, most commonly used rack because it has the best compromise between sample mass capacity, acid volume, and can support rather good throughput in a nutraceutical laboratory. So some samples may be difficult to run in these. Let's say you had something such as a large fish oil capsule. I have actually digested full fish oil capsules in the ultrawave with some care. We do know how to do that, and I've done it successfully. We do have larger vials. This is part of our 5-position rack. I can take this fish oil capsule and digest this in here. Together with, using this mixed rack, I have a turmeric sample, which can be reactive with nitric acid, and I also have a calcium. All of these samples I can run differently. I can run together using a single microwave program. So let me show you putting this into the ultrawave. So take my samples, I'm going to hang them right from the top here. This is the same terminal with the same library of methods. What's really nice with the ultrawave is because you can do mixed batch samples, you can choose essentially 2 different microwave programs if you wanted to in your lab. Use one for easy samples and one for the difficult organics that may be reactive. I've already loaded something in here. So on the terminal, I'm going to lower down the ultrawave. Once it goes down all the way, I'm going to clamp it. I'm going to press start. Now, since I have the automatic gas module here, something I do recommend for an easier workflow in your lab, that's going to fully automate the nitrogen filling process. So that's actually going to happen right now. So with a setup like this in your lab, once you press the start button, you can go away and do something else and come back when that light turns green. Then you know your digestion is complete. The system will automatically pull down the active cooling from the chiller. The chiller not only keeps the reaction chamber at a safe operating temperature, but provides that active cooling. You can go from 250 Celsius down to pressure released in about 20 minutes or so. Once the system's completely released, you can look at step number 6 on the right. We're going to go ahead and open up the reaction chamber and dilute up the samples. So thank you very much for your time today. I do want to just summarize some of the topics that we went over. We did go over a lot. Of course, making sure you get quality analytical data all starts with the sample prep part of your process. So you want to make sure that you get a good digestion, which will give you good results on your Agilent ICP-MS. You want to consider a few different things when you're choosing the right system, not only sample types, temperatures, and pressures needed, but also throughput. How well will the system work in your lab? You don't want this to be a bottleneck, but you really want it to be a tool that helps you with your analysis. We do have 2 different platforms. We have a rotor-based microwave. The rotor we suggest for nutraceutical laboratories, our Maxi 24HB can accommodate pretty much most types of nutraceutical samples. If you ever had to work with a more difficult sample with a rotor-based system, we also do have our SK15 high-pressure rotor. Great thing about the Ethos Up is it's highly flexible and can be configured to use all 3 of our rotors, the Maxi 24, the SK15, and also the Maxi 44 if you needed it to. The UltraWave is going to be really that next step up in productivity and workflow. No vessel assembly or disassembly. You can mix batches if you need to. It's going to automatically release the pressure, and really a lot of the workflow and hands-on is going to be much more streamlined. So that really does save a lot of time in how many samples you can process in a day. We also have, in a case that your sample was a bit more difficult, you may have something such as a fish oil capsule or something higher mass that the 15-position rack or most common rack may not work for. It's easy enough to get and use our 40-position vials. And the cost of different racks to accommodate your needs is also much less expensive than getting different rotors. So I'm happy to have a one-on-one discussion with any of you if you'd like to learn more about the technology or see how maybe we can help your needs specifically. We can use the same virtual tool. I can do this on Zoom, Teams, and WebEx if you like. Hope I was able to really educate you and you have a good idea of maybe which technology might work best. Next, you'll be hearing from our Agilent partners. They have excellent technology. You'll be hearing from Craig Jones, ICP-MS specialist with a lot of experience. So I'm going to pass it over to him and leave you in good hands with that. Thank you very much, and have a wonderful day.
Thank you, Eric. Before moving on to our next talk, we have a quick poll for you that I'm going to initiate right now. The poll is, which of the following best describes how your lab processes samples for trace metals analysis? We outsource our samples to external labs. We currently analyze samples in-house. We plan to analyze samples in-house in the future, or no plans for trace metals analysis. I'll give everyone just quick 30 seconds to finish this, and then we'll move on to Craig. Okay, great. So Now I'm going to move on to Craig Jones for our next presentation. Craig will discuss ICP-MS and how to set up your system to get the most out of your workflow. Please take it away, Craig.
Hello, everyone. My name is Craig Jones. I'm an ICP-MS application specialist here at Agilent Technologies in Santa Clara, California. And today I'd like to talk to you about our new 7850 ICP-MS unit that's sitting here behind me. It's added to our portfolio of ICP-MS, which includes the other single quad system, which is the 7900, and also our 8900 triple quad ICP-MS. This system is hooked up to our standard SPS4 auto sampler. We can fully configure the racks, so we've got 21 position, 60 position, we can add 90 position racks in here, even make a more high volume rack in the center as well. As you can see, it's also enclosed, so that minimizes on any laboratory contamination from the ambient air, and it's also vented so that we reduce the acid accumulation inside the unit itself. We do need to use a chiller, and the chiller, if you can see those gray lines that go up in the back, that's located in a room next door, just to minimize on the heat and the noise that it can contribute to the laboratory as well. Down here to my right is where the rough pump is located, and that rough pump is actually in an enclosure, and that's to help reduce the noise as well. We like to have the rough pump close to the system, so that's why it's located right next to the instrument. Cell gases are located behind the instrument. Some of them are located in the room next door, and that's pretty much all you need. The argon, of course, we've got a bulk argon system, and that's located down the hall. So let's look a little bit closer about the hardware on this system. So the sample is drawn up by the probe. You can see the probe there in the very back, and it's pulled up by a 3-channel peristaltic pump. We've got our sample line, our internal standard line, and our drain tube. The sample and the internal standard are mixed together using this grounded mixing tee, and then they're brought up to the nebulizer. In this case, we're using a micromist nebulizer. It's a pretty standard nebulizer we use for most applications. I use any high matrix type applications to super clean applications. Just depends on what you need. You can configure it for other nebulizers depending on what your application is. Right behind that is where the UHMI is located. I know it's a little bit difficult to see, but that's what creates that aerosol dilution, so we get a very robust plasma. So if we're running high matrix samples, that will help reduce the ionization suppression within the plasma itself, and so that we can run up to 25% total dissolved solids. The spray chamber is enclosed in the Peltier device, and we cool that down to 2 degrees for most routine applications, and that helps minimize any large water droplets from getting into the plasma. That creates a much hotter plasma as well. It's important to have a hot plasma. That way those elements such as arsenic, mercury that have very high ionization potentials are ionized more effectively. Let's open up the torch box. Inside the torch box, here's our cover. And you can see most of the things are just simple clamps. You don't really need any special tools to access the torch box. Here, the torch is just clamped down simply. And this is a 2.5 millimeter ejector torch. That allows for, that larger orifice allows for longer residence time in the plasma. Again, that helps reduce matrix effects on the front end, ionization suppression, and also allows for longer residence time in the plasma. So it's breaking down some of those polyatomics before they even reach the cell, which we'll talk about in a minute. In order to access the cones, if we're going to do any maintenance on the system, there's this little button here where my index finger is, and it slowly moves the torch out of the way. The stepping motors on this are 0.1 millimeter accurate, so I know that when I move it out of the way, do my maintenance, and pull it back, it's going to be in the exact right position. To access the cones, simple as taking off this retaining ring, and there's my sampler cone. This is a nickel-plated sampler cone. We have many different choices for cones depending on the acid matrix that you're running. You know, higher acid, more aggressive acids. You might want to use a platinum cone, and then we do have just a base nickel copper cone as well. Right behind that is our skimmer cone, and then that's attached to the lens assembly. So here's an example of our cone. That's our skimmer cone, and it's just attached right in the front end. And in this case, this is an X lens assembly. The X lens, as the ions enter here, they're deflected by this omega lens, and that's a very gentle bend. And the reason we do that is to stop the photons and neutrals from entering the system to fatigue the detector. So it gives us a much longer life on our detector. The other thing that I'd like to mention is the fact that since that is a gentle bend, it's not a radical 90-degree bend, is the fact that that gives us much better low mass sensitivity. So as you can imagine, the lighter masses get pushed to the outside of that collimated ion beam, and if they have to go around an aggressive corner, they might actually just fly off of the ion beam. So this keeps them intact so that they enter the cell as well. We're talking about elements like lithium, beryllium, boron, all those light mass elements. All right, so after the lens assembly is where our cell comes in. And so the ions, after they go through that skimmer cone, they enter into the cell. We bleed helium mode. We can also have a hydrogen mode if we do need low detection limits for just a handful of elements, but typically helium mode is the way to do it. That helium then knocks out those larger polyatomics that interfere with the associated analyte of interest, slows them down because we have a little bit more positive on the back end so that only the analyte will exit out of the cell. Once this exits out of the cell, it goes into our quadrupole. And the quadrupole is, of course, directly behind the cell assembly. And then right behind that would be our detector. And then that sends the signal to the system. Our detector is 11 orders dynamic range. So at the same time that we're looking at trace elements, we can also be analyzing ppm levels, even percent levels of some elements as well. So to put everything back together here, I'm just going to put the cone back in, tighten it up, press the button again, and the system will move back into position. Go ahead and replace the torch box cover. And there you go. So that's basically the hardware in a nutshell. Now let's talk about some of our platform software, which is called ICP-Go. Okay, so now that we've seen the hardware on the 7850 ICP-MS, let's talk about our platform software called ICP-Go. ICP-Go runs on top of our master software to give you ease of access, remote access to the analysis, and makes it much more simpler for an entry-level technician to set up and run the instrument. So the batches are created, and the elements are specified, the associated plasma conditions are specified, and then we also specify where the standards are going to be located and the associated QC. You can see here, this just gives us the hardware information so that we know where everything is set up and that we're using, the right auto sampler, the right ion lens model, and then that we're doing everything in an aqueous solution. I've actually started a run right now, and you can see at the bottom, for that associated batch, it's doing an auto tune. So it's optimizing the lens voltages to make sure that we have the best sensitivity. So this is important if you're running several batches into the evening. We can do an auto tune right prior to recalibrate, and it's just going to optimize those lens voltages, give us a tune report, and then start the calibration and start the analysis. Now, I've obviously already started the plasma up here at the top right. The plasma is blue, so that means that it's on. But when I first came in, I ignited the plasma, and what the instrument did was it went through a warm-up period, and then it went to a tune solution, and it optimized the system based on Agilent specifications. So it made sure that the instrument was as sensitive as it could be and that we're ready to go. Once it was done with that, it spit out an instrument test report or a performance report. And that's what we have here. And so this gives us our sensitivity readings, our stability or RSDs, resolution and access settings. And then it also gives us the plasma conditions, lens settings, and then hardware settings as well. It also goes so far as to take every meter reading on the system. For some reason down the line, things started to look a little erroneous. Then a service engineer could look at this data and say, oh yeah, it looks like this parameter has changed. This is how we're going to address to resolve that problem. And then it also takes a snapshot of all the previous performance reports. So you always get this historical data. Once this performance report is complete, then we know that the instrument's healthy, and we know that we can start creating batches. So let's do that. And again, I've run an analysis so we can look at some data, and then I've got one running right now as well. And it should be putting out a tune report here soon. So if we add a batch, we could go to the template list. So you can see here I've got several different ones that I do on my ICP Go. But let's do a Nutra full element suite today. So I want to double check and make sure, hey, are these the right elements for the samples that I want to run? So I can look at the periodic, and at a glance, I can tell that everything that's in blue here, those are my analytes, and everything in purple, those are my internal standards. So I can confirm, yep, this is the analysis that I want to do today. I'm going to go on ahead and go back. Now, here's our calibration standards. So remember I was saying we always put our standards in the same location on the rack on a day-to-day basis. That's typically what people do. So that tech would, prepare the calibration standards, put them in the associated rack positions, and that also goes for the quality control samples as well. And those are automatically going to run every 10 samples. We've already set that up in the base position. They don't need to do any of that. All they have to do is enter the unknown samples. Now, we can do this two ways. Probably the simplest way would be to import it from a lens so that you have all of the information that you want on your sample list. So sample ID, what the sample type is, and then maybe if you want to include the digestion information, how many grams were used, what the total volume is, and then any additional dilutions you might have done. So that would get pre-populated into the system from a lens. The other way that we can do it is we can just add samples to this block. So if I click on here, I first see what's been populated. So these occupied positions, if I hover over the top, it says, well, that's the health standard. Great. Oh, it's over here. Oh, that's where my secondary control standard is located. So I can't put samples there. That's great. Well, I'm going to add about 14 samples to this analysis. I'm going to put them in rack number 2. So you see how it just populates them, right down the row into the next column. Click on OK, and now it gives us that list. We can still edit this. I can change these sample names, sample X maybe. And then if I want to change the type, so let's say I know that I spiked a few samples. So sample X is actually going to be spiked. So I'm going to go ahead and say, you know what, I'm going to make that a spike. And so that way, in the software, we set it up to give us recoveries, then we can check everything out. Okay, I'll shift gears here real quick. Since it's running that other report, it went ahead and it auto-tuned it. So now here's the tune check report that's associated specifically to that batch, because we might have different plasma conditions. So it looks at the RSDs, the associated elements, background levels, quad positioning as well, make sure all that passes. It would flag it on here on the right if anything was out of compliance. And then, of course, it gives us the plasma conditions, and it also gives us cell parameters and hardware settings. So I know that my tune report is good. The instrument was tuned well, so that next batch that's going on is going to be good to go. So let's go back to create a batch. So again, if we're going to do spikes, all of these, we're going to look at the recoveries, and we're going to see how the ICP Go software calculates those and displays them. Pretty simple, right? We'll just give this a new batch name. We'll call this Demo 2. going to go ahead and save that. And now it's going to, I can add it to the queue. Now look at the bottom right now. It's starting to do the calibration, and it's automatically tuning the detector for pulse to analog. That's what gives us that high dynamic range. So since it's tuning from pulse to analog, if the signal intensity gets too high and the detector switches to analog, we're going to get a nice linear curve. We're going to get a nice linear response from pulse to analog. So that's what gives us the ability to analyze things that are in ppm, even percent levels, at the same time that we're analyzing trace analysis. All right, so number 2, you can see over here in the queue, we're set at 1 right now. So I'm going to go ahead and add that, and that goes to 2. So now we've got these 2 batches that are going to be run subsequently. Let's look at the batch that I already ran. All right, so this is the full element suite. Well, unfortunately, it's red, so I can see that very far away. You can see that it was red. Well, that means something went awry, something failed. And sure enough, we look, it's completed, but something failed. Well, first thing I'll look at is my internal standards. So I can easily go look at the internal standards display. Well, those look great. They stayed really stable throughout this short analysis that I did. So that's not the problem. Well, I don't want to scroll down through every single sample in the batch, so I'm going to filter it. All right, so, well, it looks like that secondary control standard failed for some reason. Let's look at the results. By going into here, I can look down and I can say, where's that failed sample? Oh, there it is. And it's barium. So you see that it's at 526 ppb. Well, I know that that is actually passing for this mixed, this associated mixed standard that I ran. But on the right-hand side, you can see that that concentration value is over that calibration range. So as we just saw, as it's doing the calibration, it's calibrating the detector for the pulse to analog signal. So what that means is, since this passed, I know that I have a very linear curve, even though I only calibrated up to 100 ppb, but I'm still getting good recovery on a sample that's 500, just over 526 ppb. If we look at all these samples, we can go back here. Let's go back again, and I want to just look at the associated report. We have a multitude of reports. So this is another way that we can look at this data. So I can actually look through here. We can edit this header. You can add to the header or delete from the header information. We can also look at the table where we've got concentrations, counts per second RSD, so on. It shows us the detector that it used to acquire those that data in, and then it also gives us the internal standard recoveries as well. So a lot of companies like to have a PDF report for this, or even a hard copy report, send it to a printer, in addition to the data that you can see displayed within the ICP-Go software. So let's go back here again. Let's look back at our NIST sample. And the other thing I wanted to mention is, since we're doing nutraceutical, we're really concerned, the big four, sometimes we're concerned with maybe some of the major elements for proof of labeling or whatnot. But I did analyze for mercury, and mercury needs HCl in order to be stabilized within the calibration. And we get a nice linear curve here. This looks great. I calibrated up to 2 ppb, and you can see when I hover over that, it shows up at the top what concentration was entered, and then it back calculates that concentration. So my 2 ppb read back at 1.988, so it's within 2%. The other thing, it gives us our linear regression, and it also gives us the associated detection limit here at 7 parts per trillion, and our background equivalent concentration. If I wanted to, if I started to look at my samples and I saw that something had failed, maybe an internal standard, well, it looks like in that unlikely case, an internal standard is present. I could actually change that and reprocess the data. That's really the only thing that the analysts can do. If they see that and, maybe run something that had scandium in it, they could reference it to a different internal standard and then recalculate the data. But all the technician can do in here is that and add samples to the run. That's it. So the other thing I want to mention, since we're doing HCl, we get a nice linear curve, we had to use HCl. Well, HCl causes an interference when it combines with argon and makes argon chloride, so we can't analyze for arsenic. Well, since the helium collision cell works so well, to remove that argon chloride interference, I get a very nice curve for arsenic, and I got a detection limit of about 50 parts per trillion. So just wanted to mention that we can run arsenic and mercury at the same time in the same round, as well as all these other elements also. All right, so let's go ahead and look at the entire data. Everything is set. So we know that everything is good to go. And we can also, if we go on ahead and we look at that queue, we can see what's going on. The other thing is, if I wanted to, I could select an item. If I had multiple, if I wanted to, I could actually select one of these and I could say, you know what, I want to move this up or down in the queue. So if you had multiple batches that you're in your office and you realize, oh no, that sample set that's being run, fifth one down the line, I need to get that data out the door. You could position it up into the queue so that it's going to be run next. The other thing you could also do is you could actually go in here and you could say, you know what, I want to edit this sample table so that I can actually add things to the sample table. So I can actually add new samples so that those would be set up and ready to go so that I can prioritize and make sure that I'm getting data done as quickly as possible in the best time frame. So with that being said, that's ICP Go. I hope if anybody has any questions, they certainly let us know. And thanks for listening. Have a great
Thank you, Craig. Now to share, actually, sorry, I'm going to share the results of the poll after the Q&A. We are still tabulating everything. But for our final topic today, we will have Emmett present on issues of CFR compliance. He's going to take it away here right now, Emmett, and share his slides.
Thanks, Ryan. Let me get this presentation up here. Oops, let's see. All right. Is my screen active?
Yes.
Okay, very good.
Well, Emmett.
Okay, great, thank you. All right, well, hello everyone. I am going to just give you a brief overview of compliance, specifically when it comes to ICP-MS and what Agilent provides. And what I did, just for those people who are not familiar with what's required in compliance, actually, what is compliance? I just did a quick Google search and typed in 21 CFR. And this is sort of a brief overview, just a brief description of really what compliance is. And compliance is also, we refer to it as 21 CFR or Part 11, or sometimes we refer to it as a regulated environment. But really, it is it's the code of federal regulations and the FDA regulations on electronic records and electronic signatures. And really, what it applies to right now are drug makers, manufacturers of medical devices, some other biotech companies, things like that. We've seen some of our customers and even some of our cannabis customers adopt adopt 21 CFR either completely or partially. And the whole purpose of 21 CFR is just to ensure data security, integrity, and traceability. So there are 4 components to compliance. And again, I'll use these terms interchangeably: compliance, regulated environment, part 11. But there are 4 aspects of it. The first part of it is what we call IQ and OQ on an instrument. And that's really to assure that when an instrument is purchased, it meets the design requirements, the intended use requirements from the IQ, which is installation qualification standpoint. It makes sure that all the site prep documents, the installation documents, the reference and user manuals are all available and all recorded, and that the software is installed correctly. From the OQ standpoint, which is operational qualification, it does things like make sure that the instrument is performing as per manufacturer specifications and that everything is working correctly, auto samplers, all of that. So this is really making sure that whatever instrument is being used, whether it's ICP-MS, GC-MS, GC-LC, whatever, that things are installed and operating properly. Then you have what's referred to as access control. We want to make sure that only certain people have certain capabilities to log on, and that there's secure access to log on and to run batches or to modify methods. Different users have different capabilities. And then what we have to do is we have to store those records in a secure environment with access only to certain people, and some other things that I'll address here in a few more slides. But really the whole purpose there is to make sure that once that data is acquired, that only certain things can be done to it and that there's an audit trail on all of that. And then lastly, we've got limitations on the physical access to the instrument, basically locked doors, key cards, things like that to get in. So all of this here, of course, item number 4 is something that the specific laboratories or facilities would have to do. But items 1, 2, and 3, well, Agilent provides the services and the software products to do that. So when you look at that, we have Mass Hunter, which Craig touched upon. He was looking at Mass Hunter, or demonstrated Mass Hunter accessed through ICP Go. We have Mass Hunter as the, of course, acquisition and data processing software. We have user access control, which we configure to do audit trails and to give certain users different permissions as far as what they can do. And then we have our secure database storage. And we have a few options there, which I'll discuss briefly. So again, looking at this in a slightly different way, here's the Mass Hunter software. This is where we acquire the data, we process it, and we can modify the data if need be. We can change internal standards like Craig showed you in ICP Go. But then we have to actually look at our first step of compliance. Now, first step of compliance, as far as software goes, is access control. And this is where our user access control software comes in with our open lab shared services. And again, without getting into too many details here, just as an overview of what UAC does, it first activates the functional link to the ICP-MS Mass Hunter software and compliance software. Now, again, we've got a few different options for compliance software, but UAC provides that link. It also activates Open Lab shared services, and this is where we can configure groups and users And these users and groups, they all have different roles. For instance, somebody can log on as a lower level user and have the ability to change a sample list. In other words, to load a batch of samples for that day and run samples. And that's all the capability they have. Whereas other users might have the ability to modify a method or to modify data. So there are different permissions that are granted to different users. It also activates an audit trail. So that means if somebody changes an internal standard, they have to say why they changed that internal standard. It's noted as to who was the end user actually making that change and at what time when that was done. So that is our user access control software. And again, that is the first step of compliance from a software standpoint. Then the next step is securing that data. Okay, that data has to be secure and it has to be accessible only by certain people. So what we have pretty much are 3 or 4 levels of remote data storage, or I should say data storage. The most basic version of that is what we call SDA, that is the Spectral Database Administrator, and that resides on the local PC. So it's installed on the same computer as the Agilent Mass Hunter software, and that supports only one ICP-MS. It can also be used for optical ICP as well, ICP-OES, but it supports only one instrument. And everything is local. It's all done through a Microsoft SQL server as far as search and retrieval of data. The data is encrypted and it's stored in secure directories. But again, it works only for one ICP-MS or an ICP-OES. Then if we move up a little bit more in capability, we have what's known as Open Lab Server. And by the way, these 3 options here are server-based. An Open Lab Server is nothing more than a data storage medium. It is a secure data storage medium. Everything has to be accessed through SDA in order to retrieve that information, but it is secure and it is a remote server. We can move it up another step. Oh, and I should mention here, once we get into these server-based systems, we can start adding more instruments. We can actually have up to 100 instruments on Open Lab Server. But again, this is nothing more than a data storage device. If we move up another notch, we have what's known as Open Lab ECMXT, and we can start taking in information from up to 100 systems, again, just like Open Lab Server, but we can also access reports. We can actually view some of the data and we can generate reports from that application itself. And then lastly, we go up to the full-fledged Open Lab ECM, and that has a lot of capability. It's got advanced retrieval and reporting functions. It also has the ability to take in data from non-Agilent instruments, non-Agilent LCs, GCs, things like that. It also has the electronic lab notebook and many other features. So basically what we try to do is provide compliant solutions for anywhere from the smallest lab with one ICP-MS to the bigger labs with LCs and GCs, and really to the major pharma companies, with global facilities. So that's sort of an overview of our compliance solutions. Thank you very much for your time. I can turn this back now to Ryan and certainly open the floor to questions.
Thank you, Emmett. So before we jump into Q&A, just want to broadcast the polling results really quickly for everyone. And as you can see, the vast majority of you are already doing this analysis in-house. So hopefully you guys can find this to be helpful to optimize what you guys are currently doing as part of your workflow. And now on to the questions. I invite Eric, Craig, and Emmett to join us now. Great. I'll get us started with the first question. Let's see. All right, Eric, this one's for you. How does sample throughput compare for rotor-based microwave versus the ultrawave with SRC technology?
Thanks, Ryan. That's actually a really good question. So with the ultrawave, you're able to get about twice the throughput you can with a rotor-based system, and that's because of a few things, particularly with the workflow. You're going to save a lot of time from so the ultrawave, remember, you have no vessel assembly or disassembly, so you take that loose-fitting cap, place it on, take it off when you're done. Rotor-based systems, you do have to manually depressurize them under the fume hood. Also, the ultrawave does utilize an active cooling with an external chiller, so that will rapidly cool down and depressurize. Compare that to a rotor-based system, where the system is going to cool the rotors by air passing across it, but you still have to manually depressurize each individual reaction vessel. Another thing that's great about the ultrawave is it does have the ability to use disposable borosilicate glass vials. So that means if you're using those, you can simply throw them in the garbage when you're done, and there's no need to clean those vials.
Great, thanks, Eric. Next question, this is going to be for the Agilent team. Is it possible to determine elements for proof of labeling while also determining the low-level toxic elements?
I'll take that one. It certainly is. So as I mentioned, we have 1100 dynamic range detector, and so we can look at ppm percent levels of things like sodium, magnesium, calcium, and at the same time in determining those toxic elements, arsenic, cadmium, lead, and mercury. So.
Another question for the Agilent team. Can ICP Go work with compliance software?
Oh, okay. As it turns out, no. You have to work with Mass Hunter directly. One thing I should mention, and Craig asked me to mention this, ICP Go is a web-based application, and you're actually making your Mass Hunter computer. You've got a shell that overlies Mass Hunter, and that is ICP Go. And you're actually setting up that computer as a server. So you're logging into ICP Go from any device that's running, that can run a web browser. It's actually a browser-based application. But unfortunately, at this point in time, you have to use Mass Hunter. You cannot use ICP Go and be compliant.
Next question. Eric, this one's for you. Is there a difference in the sample mass you can digest in the Maxi-24 as compared to the SK-15?
Yes, so the SK-15 is our high pressure rotor, and the Maxi-24 HP are high performance rotor. So the answer to that is yes. For the Maxi-24 HP, you're going to be up to about 0.5 gram sample dependent. That really depends on how much pressure is generated during the digestion process. So that's why we would recommend the Maxi-24 HP for most of what you're doing in a nutraceutical laboratory. However, if you do have to digest, say, more than 0.5 gram, closer to 0.75 gram of some of those higher organics, that's about where you might want to start to use the SK-15 high pressure rotor. Great thing about the Ethos Up is it can be provisioned to use both the SK-15 as well as Maxi-44. Easy enough to just take one out and put one right in.
Excellent. I'm going to do 2 more questions. I know we're running a little bit long. First, can all elements be analyzed in helium mode, or do I have to use different cell gases for different elements?
You can take that. So yes, everything can be done in helium mode. So what I do for the light mass elements, I just increase the integration time. And really the heavier masses aren't that as affected by the cell gas. So if you need high throughput, you want to use just one tube mode, that's great. No problem whatsoever. Now, if you need elements like selenium or calcium, probably not for nutrients. We do have hydrogen that we can add there too for just a handful of elements. But helium will serve you well for most of the applications, especially in Nutra.
Great. And last question for Agilent as well. What type of information will I be able to get from the ICP-MS's audit trail?
Okay. All right. Yeah, I'll take that one, Craig. Yeah, actually, it is. It's very detailed. If anybody changes a point on a calibration curve, if they change a method, of course, that person is logged on as a user. It's keeping track of who's doing it at what time. And that's from the ICP-MS Mass Hunter standpoint. Also, from the Open Lab Shared Services standpoint, you can track who's been on and for how long. You can track which users have been created, what kind of capability they have. There's a lot of information. Basically, anything that's done on the system is tracked, and it's time-stamped, and it's verified who's done it. And oftentimes, depending on what kind of changes are being made, you have to enter in reasons justifying why you're doing that. So it's a very complete kind of audit trail from both the analysis standpoint and the configuration of users and the amount of time users have spent on the system. So there's a lot of information in that audit trail.
Excellent. Well, I want to thank Eric, Craig, and Emmett for their time today, and thank you very much for attending. As I mentioned, we are recording this, so will be available afterwards. We will send email links to all of you, but I hope you found it to be informative, and hope everyone has a fantastic rest of their Tuesday. Thanks. Take care.
Thank you.